Some sharks grow new teeth for themselves in a few weeks, and needle mice can completely heal severe burns or restore kidneys, even if they lose part of an organ. What if we could fix ourselves just like that, or even better? What opportunities do we have for this? This is a column called Chronicles of the Future. We take the latest real scientific research, discoveries and inventions, and see what will happen if we are able to put them into practice, how they could change us and our daily lives. These are not forecasts. I do not evaluate probabilities. This is an attempt to see the possibilities in what scientists, engineers are already discovering, inventing today. Opportunities can and will change with the advent of new research and development. The future is constantly changing, but it always starts today. So we are already living in it, even if we don't notice it yet. You come to the dentist like that, and then he says that you need to remove a couple of teeth. You nod, no problem. You immediately prescribes a course, a couple of months of injections, and new, native ones grow on the site of the removed ones. We will have to wait, of course, but there are no bills for hundreds of thousands of painful procedures, with screwing titanium implants into the gums, and the risks that they will not take root, and we will have to redo everything or worse. So now in Japan, preparations have begun for the world's first clinical trial of a drug for tooth regeneration. They will test on people what already works on mice for sure. The main question is whether it will not work now, and whether there will be dangerous or unacceptably harmful side effects. They will be tested on the most desperate volunteers with a very rare genetic disorder, namely the genesis of teeth. It leads to the fact that a person does not grow several or even one tooth since childhood. The scientists' solution turned out to be elegant. At first, they tried to break down directly and affect the molecules and mechanisms in the cells that are involved in the development of teeth. But it turned out that they are also critical for the development of bones and other organs. Experimental mice simply died when scientists tried to force their bodies to grow new teeth. Then we looked at the antibody, which, on the contrary, inhibits the growth of teeth. After all, if you do not restrain at all, then the opposite can happen when you do not know where to go from extra teeth. Teeth can climb the second and third row. I warn you, Google hyperdontia pictures exclusively at your own risk. I will not show it. Researchers have learned with the help of an antibody not to let go completely, but to loosen the leash a little and let the missing teeth grow up without uninvited excitement. Look at these brand new teeth in rodents. In different experiments, the method was reproduced by different teams of scientists. If human trials are successful, then we can get medicines for growing teeth by the early 30s. Now back to the future. The dentist won't let you go yet. You haven't been checked for too long. Yeah. There's a chip, there's already a serious hole. But they don't put fillings on you, they just cover the damaged teeth with sealed caps and let them go. A couple of weeks will pass, special cells will develop enamel in worn-out places, and worn teeth will be like new. And what is in reality? A study was published in which the authors taught the teeth what our teeth have forgotten how to do today, to produce the most durable material in the human body, enamel. After the teeth mature, the process stops or proceeds so little that all these advertisements about restoring tooth enamel with toothpaste are literally a hoax. To really restart the process, the scientists had to grow teeth from stem cells in a test tube. Biologists activated certain genes, and universal cells began to turn into specific ones. And meloblasts are the very cells that produce enamel in our body when teeth are just developing. But such production is curtailed when the teeth reach the condition. So, in a test tube, the researchers turned out, of course, defective teeth. And organoids are structures of cells similar in properties to real ones. And they produced 3 proteins. And already from these proteins, a tissue like enamel began to form. It is not yet the enamel itself, but a mineral substance close to it in composition. This was the first time we managed to pull it off, so there are plenty of opportunities to optimize the process. This brings us closer to making living fillings a reality. Not a material for plugging holes as it is now, but some kind of repair masters at the cellular level who will restore everything themselves, and you will not have to grow your teeth again because you did not keep track of caries. Back to the future. There's a call for you. The patient's heart is failing. He already had problems with it, and then he got into a serious accident. We need a transplant. He asks, do you want to put a ready-made heart or make a new one yourself? You understand, there will be fewer risks with the new one, but more time is needed, but it doesn't burn. You say, you start doing new things, and drive on through traffic jams. Colleagues connect the patient to a life support system that will support the body's functions normally before the transplant. The operation will take place in the evening. Meanwhile, skin cell samples are taken from the patient. They are processed and placed in a bioreactor. It is necessary to increase the amount sufficient for a new organ. You deal with other patients all day, and in the evening, you return to the same one. A mass of cells is taken out of the bioreactor and added to a flask with a hydrogel. It is irradiated with light for 10 minutes, no more. And the chips can be taken out of a new living heart ready for transplantation from the cells of the patient himself. This means that it will take root without problems. You don't go to the operating room, sit down in the next room at the monitor, take the controller as for video games, and watch the manipulations of the robotic arms controlled by the neural network, the surgeon. She does everything by herself, from the initial incisions to connecting the arteries and suturing. Human assistants help her. It is too expensive to transfer everything to automation, even in the future. You will intervene at any moment if the surgeon starts doing something wrong. But everything goes quickly, and this radically reduces the risks for the patient. He will recover much faster than after a traditional long transplant operation. And for you, such efficiency is good because the shift has already ended and it's time to go home. So we are already very close to such a future. Now, one after another, studies are being published that solve the problems of printing organs from living cells, which previously seemed so difficult that they were almost insurmountable in the foreseeable future. The Medical University of Innsbruck has a whole laboratory for three-dimensional printing of biological objects. Her team has been printing skin from living cells for the last 10 years without any problems. But why can't scientists still make the heart, liver, or brain, at least some parts of it, in the same way? The head of the lab explains, "I have zero German, so I had to use Yandex neural networks browser. One problem is just the number of cells. If we imagine that the human heart consists of 100 billion cells connected to each other in a certain context, or in certain relationships, and interact with each other, 100 billion cells, if we take such a Petri dish, we will get 5 million cells inside. That is, we will get about 20,000. Such Petri dishes are needed to print a human heart. The second point, of course, is that the organ in our body has been growing for years and decades, and the cells that sat there, or that formed the organ, leave behind a protein framework, so to speak. And then, when this individual cell dies and is replaced, it leaves a more or less small note about what the successor cell should do there, and in what direction it should develop. And of course, you can't recreate that with a 3D bioprinting. The scientist gave this interview 2 years ago, not knowing what would happen next. And that's what we have today. Now you can see how the liver is imprinted from a mixture of hydrogel and living cells. The process takes a little less than 5 minutes. The organ has a vascular system. It can be seen through the lumen, and here living cells are clearly visible. They glow green. Dark is a hydrogel. Of course, it's a little early to transplant such a thing to a person. The authors of this study themselves call it only a model of the liver, but they have proved that it is possible to print a complex and large, three-dimensional structure of living cells, the size of a real living organ, and most importantly, so fast that the cells will not have time to dough. This is a very serious problem of many more familiar types of three-dimensional printing, low speed, and mechanical loads. By the time you reach the end, the first cells will already die from lack of power, or not all will survive passing through the printer nozzles. But we still need to achieve high resolution. What's the point if you print in lumps or only large fragments without nuances, approximate in the shape of a heart, with approximate vessels in shape, and will work approximately? Therefore, the technology that solves all these critical tasks is rapidly developing now, volumetric bioprinting. It was with her help that the liver with blood vessels was created, or, for example, a hand. It was done in just 19 minutes. Living cells are added to the hydrogel, which will serve as a material for the skeleton of the organ, and at the same time protection from the external environment, and begins to irradiate with light of a certain wavelength, from which the gel hardens. This happens immediately in volume. You get the right shape layer by layer. We still can't make ready-made organs like that, because it's not enough for cells to take up the right places. We need them to start doing in their places what they are supposed to do there, and most importantly, together with the others. To do this, it is necessary that the cells themselves are sufficiently mature and functional and cooperate with their neighbors. But you can transplant an organ with the help of a robot right now. Recently, it became known about the world's first liver transplant operation with the help of a robot surgeon. The organ was from a donor, but unlike previous attempts, the patient was transplanted, not a part of the liver, but the whole of it, because it was devoured by the tumor, and it was impossible to leave even partially. The 60-year-old man has already recovered and is still feeling well. However, the robot was not autonomous. These were two electromechanical arms operated by a human surgeon. They allow you to do everything as accurately and subtly as the hand of even the most experienced and accurate doctor cannot do. First, small incisions are made, and then all manipulations are carried out inside the body through them, which dramatically reduces the risks of recovery for the patient. Adding a robot surgeon's own intelligence, for example, with the help of neural networks, which means based on the experience of hundreds of thousands of real operations, I'm sure it's a matter of time, and very soon, autonomous robots are already operating in the same hospital where this transplant took place. So far, they just deliver things, underwear, medicines around the building, but without much control and participation of people. In general, there is a whole laboratory in that hospital where robots and algorithms are created and adapted for real medical tasks. And it's you and I who have not yet reached new research and inventions for growing body parts and whole organs, including recovery mechanisms hidden in us in order to restore muscle strength, hearing, vision, or even repair damaged areas of the brain. But before that, small reminders that all these achievements could easily not have happened if people's very attitude to the value of human life and progress had not changed. In the Middle Ages, it was considered an enviable fate to live to old age, but if a person did not die for too long, it seemed suspicious and was considered a bad sign. A person, as it were, experienced his fate for a long time, lived longer than the prescribed period, and this is unnatural. According to popular beliefs of the Eastern Slavs, those who miraculously recovered or lived to a very old age did it not because of good health, but because they took the lives of others. Today, our abilities to overcome death are changing faster than our attitudes towards it. The book Death in the Big City tells about this fascinatingly. This is an exclusive of the Line book service from MTS, so only they have electronic versions. Do you want to know how a forensic psychiatrist gets into the minds of violent villains? Check out another exclusive of the Line's The Book Criminal Mind. One click. Here it is in audio format, so it is more profitable to buy any of the subscriptions at once. There are several of them, depending on how you read, a little bit, a lot, or more of all. Non-fiction, serious fiction, children's, teen, comics, mango, and much, much more. Download the reader, and everything is with you. According to the promo code SAVEN, you will have 30 days. There are a lot of subscriptions, so try it boldly. Get intellectual and aesthetic pleasure. You will definitely find something for yourself. The link to the application lines in the description under the video. If bioprinters fail to make mass technologies for everyday printing of whole organs and body parts, don't worry, we have a backup plan. Imagine a special patient comes to you. He has lung cancer in the last stage. He did not notice until the last. Metastases have already spread to all the lungs, but they have not gone beyond. Only a transplant will save you. You log into the Organ Donation Bank app and place an order as the attending physician. Within an hour, a suitable set of lungs is delivered to you. How? Just the other day, specialists from the Maryland School of Medicine performed a complex operation to transplant a pig's heart to a human. The 50-year-old patient was doomed. His heart was running out due to a serious illness, along with major vascular problems, and in addition, complications in the form of internal bleeding. There was no time to wait for human donors, and they had to happen either right now, or our patient could already become a donor. Currently, a heart transplant should be performed within about 4 hours after the donor's death. The lungs have about 6 hours. And all this is subject to very high-quality storage of organs from the first minutes after removal and during the entire transportation. Right now, we don't know how to freeze organs for months, weeks, or at least 4 days, and defrost them when it is necessary for transplantation. But here he is, Lawrence Fawcett, after the operation, the second person in history to have a pig's heart beating in him. Happy himself, next to a happy wife. So animals can become mass suppliers of spare parts to save human lives, destinies, and families. So that you understand the scale of the problem, in the most advanced countries, up to 40 people a year per million of the population become donors. This indicator is the leader of statistics in Spain. In Russia, there are only 10 donors per million people per year. This is official data, and hundreds of thousands of people need transplants every year. Some, as in the case of the kidneys, can wait, and they are on the waiting lists. Who is very lucky, a couple of years. Who is not very lucky, 5 or 7 years. It holds only thanks to the dialysis procedure, when a special device performs the work for the kidneys. So, the world needs the technology of mass production of new spare organs. You may have heard that the first patient to whom the heart of a genetically modified pig was transplanted lived no more than 2 months, and it might seem that the technology is questionable. And only a year and a half later, quite recently, a study was published which examines in detail what went wrong. The problem turned out to be not so much in the organ from the animal, but in how the patient was treated after the operation. Even before the transplant, the immune system was too weakened, and already at the recovery stage. The poor people could not inject some drugs, and even in the right volumes, and this is critically important, because they help the new organ to take root. In short, despite some problems, we solved the main problem. We learned how to grow organs in animals and transplant them to ourselves. It remains to refine the procedures for a more stable and reliable recovery, so that patients with a variety of medical histories have a more predictable high survival rate. But experience suggests that not all people will be able to put up with having animal organs in them, even if it would save their lives. And in this case, we have a serious promotion, a backup plan, if you like. A study has just been published, in which for the first time, it was possible to grow a human organ in a pig. Well, almost. We are talking about a donor, which is a chimera, a hybrid organism consisting of cells or other parts of different animals. In this case, a pig and a human. It turns out that it is possible to call the resulting creature a pigman or a pigman. First of all, it was still an incomplete being, but only embryos that were allowed to develop to the age of 25 to 28 days, and then they took it out and looked at what they got inside. And secondly, human embryos had only a few modified stem cells. They were planted with an embryo in the laboratory, in the same place. The gene for normal kidney development was broken to embryos, and after that, the poor men transplanted almost 2,000 pieces to 13 sows, where the embryos developed until scientists removed them ahead of schedule. Out of the whole crowd, only 5 chimeras were suitable for analysis. And so, they developed structurally normal kidneys, despite the breakdown, half consisting of human cells. The rest of the embryo was still almost entirely dominated by pig cells. By the way, those embryos where human cells began to take over, tried to dominate, died or stopped developing. But even if we learn how to grow organs in animals for transplantation, then there remains another problem: how to deliver them in the hospital. Without arranging a donor pig farm, where medical standards, sophisticated equipment for transplantation at every hospital or in every city. And here we seem to be witnessing a breakthrough, perhaps not only in transplantology. For the first time, scientists were able to freeze an organ, defrost it and transplant it. So far, however, the rats, but not once, but many times, and with a stable result. The tailed patients are alive. The organs have worked, even after what is called cryopreservation. This is a long-known procedure for freezing cells. So we can freeze, for example, an embryo for decades. These twins have recently broken the record. When they were born, they were already, one might say, 30 years old, because the egg was fertilized back in the early 90s, but then frozen and transplanted to a woman, the future mother, only in our days. But with organs like kidneys, heart, liver, that is complicated. This trick does not work. There is no way to defrost and get them back healthy. The problem is that there are a lot of cells in the organ, and most importantly, they are different. That is, there are no one type, vessels, muscles, and so on. They react differently to freezing. In addition, it is incredibly difficult to stop the metabolic processes in cells for the entire depth of tissues at once. While some cool down, others are still warm, suffocating, and dying. But even if the losses are not serious when freezing, the same problem finishes off when thawing. It is also uneven. So inevitably, so many cells are already dying that they begin to poison the celebration of life for everyone everyone else. Therefore, scientists in a new study have come up with a method whose names can be translated as nanoheating, and it's very similar to the work of a microwave oven. It was only necessary to figure out how to safely stuff the organ with iron particles so that they would serve as heaters from the inside to the entire depth of the tissues, which would allow the organ to quickly return to working condition. And scientists have found a convenient moment, at the stage when the liver was washed with preparations to protect against the formation of ice in the cells. Iron nanoparticles were added. The organ was frozen and thawed using a radio frequency coil, which, due to an alternating magnetic field, caused metal particles to oscillate and heat up, heating the tissues evenly and very quickly. Then, they washed the organ again, this time to clean it. Ion was ready for the transplant. Of course, some cells in the organ were still dying. If the donor kidneys recover without freezing and begin to work almost as they should within an hour after the operation, then the unfrozen ones return to normal operation for about 3 weeks. But if you think about it, until recently, we seriously did not discuss freezing whole organs. And now, we are talking about how to improve rehabilitation after thawing and transplantation. Isn't this the future, which imperceptibly becomes the present? But the most fantastic prospects for us are now opening up, where we get new opportunities to force our body to restore and renew itself. Yesterday, you were still playing basketball, and today, a friend is being taken away with a severe stroke, and you calmly write to him, as soon as you come to, call, we'll go to the pool. You know that a friend will recover in a few days, as if it's some kind of poisoning. He will be transplanted with new neurons in place of the damaged ones. Although even in the recent past, he would have been doomed to partial paralysis, or even to a state that cannot be called life at all. In a new study, healthy cells were planted in the brain affected by a serious disease in which neurons die, and they began to displace the sick until they were completely replaced. And it was not some kind of medicine or genetic program laid down by scientists, but the unexpected behavior of healthy cells. However, there are nuances. The test subjects were mice, but not simple ones, but chimeras. They had human glial cells in their brains. They are also called protectors and regulators of the nervous system, and they, human, were impaired. And then, the rodents were planted in the brain with healthy glial cells, but not yet determined in life. That is, they still had to grow up and choose a profession to become oligodendrocytes or astrocytes. But not only did healthy cells begin to take up space and literally survive the sick from there, so then, when they added the same healthy but younger ones to the healthy migrants, the young ones began to survive those who were older. That is, locally, the brain began to rejuvenate. Of course, after such a discovery, the author of the study is thinking about new types of therapies for the treatment of Parkinson's, Alzheimer's, multiple sclerosis, bipolar disorder, and even schizophrenia. Therefore, scientists are beginning to prepare materials for launching clinical trials, testing the method on humans in the next few years. Glial cells are, of course, important, but we are getting to the beginning of the beginning, to neurons. In another new study, the authors took skin cells from patients with Parkinson's, made stem cells from these cells, a procedure that has been worked out for a long time, and transplanted them to rats that have the same disease. And they discovered the moment when stem cells are best transplanted so that newcomers respond to signals from native residents, and develop into new neurons and do not understand what. So far, we have not been able to restore irreversible brain damage from Parkinson's in rats, at least in this way. But we are making significant progress in this direction due to a better understanding of the mechanisms hidden in our own cells. So, in another recent study, we found that the scars that form on the heart after a myocardial infarction can be reversed and return their cells to healthy states. And the problem is serious. Scars are formed very often after a stroke, and then seriously interferes with the work of the heart, shortening a person's life and increasing the risk of new heart attacks, which may already be fatal. So scientists have been looking for ways to rid people of these invisible and deadly scars for a long time. In the new work, the authors decided to play with fibroblasts and won the jackpot. Fibroblasts are cells that are not only needed so that we literally do not fall apart. They are involved in the formation of connective tissues, but we also owe the appearance of scars to these same guys. This happens if fibroblasts overdo it and bake too much collagen. The wounds have already been closed, and they are still piling on top and piling on top. If fibroblasts in a young body can be reprogrammed quite easily with the help of well-proven techniques, then in mature ones, they turned out to be very intractable. Scientists found what prevented them from persuading a certain gene, suppressed it, and the cells immediately became complacent and began to clean up what they had done. The scars began to dissolve. The heart completely recovered from the traces of a heart attack. Now, however, in mice, but tomorrow and the day after tomorrow, we will learn to do the same for humans. And this team of researchers, of course, is already thinking about clinical trials. The potential for regeneration, recovery, and treatment within us seems to be enormous. Only about him I hear more often from esotericists, about inner energy, some hidden forces. But if you bet on what works, regardless of how much you believe in it, that is, on evidence-based medicine, biology, genetics, then it may turn out that many drugs for the therapy of superpowers have been sealed inside us for a long time. They just got carried away by the genetic dust of millions of years of evolution. And we just need to dig them out with the help of modern tools and figure out how to restart them and not harm them at the same time. Perhaps our distant ancestors, for example swimming, could grow teeth as sharks can today. Our other ancestors probably could grow limbs or repair damaged organs. And it was neither a miracle nor science fiction. Everything was determined and is determined by completely knowable genetic, biochemical, physical processes that can be reproduced today. Or find out how they work and be inspired by them to do it in their own way and maybe even better. So our past can really be reflected in our future in an amazing way. But what we take with us from there depends only on us. Friends, if you want to see videos for a couple of days, well, sometimes a day before the release on the main channel, without advertising. Exclusive podcasts that I don't publish here are Popular Science. If you are interested in getting into a private chat in Telegram, where we informally and respectfully communicate on various topics from science and art to religion, subscribe to Saven on Patreon or on Boost. You can also click the Become a Sponsor button here. The rewards are the same on all sites. Choose what is more convenient and more suitable for you. In the meantime, special thanks. Pavel Novikov, Pyotr Kandorev, Alexandra Korotkina, Andrei Polovoy, Edie Bugger, Pavel Dunaev, Anton Polygunov, Pavel Borsky, Kopchinsk, Alyona Matsakova, Oleg Gini, Rinat Balbakov, Maxim Mendeleev, Vladimir Yemchikov, Vasilisa vs. Evgeny Balakin, Connor Livich, Pavel Valinov, 137 Hours of the Universe, Vladimir Podgorny, Alexei Shevelev, Sariga, Pavel Petryakovsky, Alexandra Aha, Stanislav Chernin, Roman Borodulio, Dmitry Shakovtsov, Vitaly Rybenko, Leonard Kusnelin, FEMA musical instrument, Azazel and Ekaterina Krapovo. Thanks to everyone who supports with likes and comments. This is also very nice. Vlad was with you. We have a peaceful sky, and see you soon.